Assalamualaikum warahmatullahi wabarakatuh. My name is Ammar. Today I will present the introduction for volumetric analysis. Introduction. Quantitative analytical method. This method is used to determine the concentration of an unknown component in a solution. Applied to the concentration of an analyte or a known solution. The method in which the concentration of a substance in a solution is estimated. This method is also known as titration and also called titrometric analysis. There is 4 categories in titration. First is acid-base neutralization. Second, redox oxidation reduction. Third, precipitation, and last, complexometry. These are apparatus used in volumetric analysis: measuring cylinder, volumetric flask, burette, beaker, and pipette. There is 5 important terms in volumetric analysis. First, molarity. Second, equivalence point. Third, endpoint. Fourth, indicator. And last, standard solution. Application of volumetric analysis. In high school and college chemistry labs, volumetric analysis is utilized to estimate the quantities of an identified compound. But there's several applications for real life of volumetric analysis. First, in biodiesel industry, to figure out how acidic a sample of vegetable oil is. Second, in petrochemical and food industries, to assess an oil's free fatty acid concentration to figure out how many unsaturated fatty acids are present and tracing amount of water. And then in textile industry, to know the nitrogen proportion in organic chemicals. In pharmaceutical industry, to manufacture product like medicine. In commercial industry, facilitates the appropriate concentration and amount of ingredient used in the manufacturing of cosmetic products.
Assalamualaikum and good evening, madam. This video is going to look at the theory behind volumetric analysis. The solution with the non-concentration is referred to as the standard solution and is prepared using a solid called a primary standard. Now, when we choose a primary standard, we have to take several things into consideration. The first one is that it should react in some sort of determinable way with analyte. So, if you're trying to determine the concentration of acid, you should really choose a base as a primary standard because it can undergo an acid-base reaction. The next thing that should be available in reasonable form is because when you weigh it out, you don't want any of that mess to be impurities. You want it to be all this the primary standard. The next thing is that stable bond in air and water. So you can store it without at sea composite, and once you dissolve it in water, it's not going to break down. One of things that we quite often remove obsolete has been used a primary standard for is because they are hygroscopic. There are two. Next, to have a larger molar mass is because you want to weigh out a high mass, not a low mass, because they will be more accurate on the scale. If the scale have a resolution of say plus or minus 0.01 or 2 gram. And the last thing we look for is that it has to be soluble in water, because most of our saturation are carried out under aqueous condition. The saturation has stopped at the endpoint, which is when the first band permanent color change is observed. So this picture up here would be a good endpoint because it's very faint color. This one down here is not because the color is far too dense. So the endpoint has been overshot. Now, if you doing acid-base titration, you need to add a indicator to determine where your endpoint is ideally. It should be really sharp. The endpoint of the titration as we get your first frame permanent color change is not the same as the equivalent point, which is when the reactants are present and they are stoichiometric ratio. So if you look at the balance equation, when you got exactly the ratio of reactant present, then your conical flux. Now this may explain that a little bit better. It is an acid-base reaction. You are starting off with acid and you're adding in base as your pH rise. So here your equivalent point will be at pH 7. When all of the acid has utilized by the base and no excess base has been added. However, might be using an indicator that has color change around pH 9. Now, as you can see here, there is really small difference in the volume between the amount of base that being at the end. So the equivalent point at pH 7 to the endpoint at pH 9.
What are a redox reaction? A redox reaction can be defined as a chemical reaction in which electrons are transferred between two reactant participants in it. The example experiment redox that we use are determination of molarity and concentration of iron 2 sulfate solution by titration with potassium permanganate. Wash burette with distilled water and rinse with CHM256 solution to permit the redox step. Next, fill with burette with CHM256 solution, record initial burette reading. Next, weight 8 gram FeSO4 and record it. Then transfer FeSO4 to 250 ml volumetric flask. Add 10 ml of 2 molar H2SO4 into volumetric flask. Add distilled water to calibration mark and shake volumetric flask. Next is pour 15 ml FeSO4 solution into small beaker by pipetting 20 ml FeSO4 into a conic flask. Step 6 is add 10 ml 2 molar H2SO4 into conical flask. Place conical flask on a white paper. Set up filtration apparatus. Titrate the solution with CHM256 from burette until end point. Swirling conical flask during titration. Endpoint indicate with solution turn light pink and record the final burette reading. Repeat titration process until 2 consecutive titration.
So here are the results of the experiment. The titration was run 3 different times, where the first being a rough titration. Now this was done so that we can get an estimated value of how much titrant to use. So we can see that we got a value of 20.6 ml of KN-NO4 used for the rough titration. Now with this in mind, we can more easily estimate the value of how much titrant we needed for the first and second titration. And as we can see from the results, we got the value for a value of 20.6 for both the first and second titration. So with this, we get an average of 20.6 ml of KN-NO4 used during the whole experiment. So in this experiment, the MnO4- is reduced to Mn2+, while the Fe2+ is oxidized to Fe3+. This happened in an acidic solution of Fe2+ plus Mn4, which results in Fe3+ plus Mn2+. So, in order to calculate the molarity of the FeSO4 solution, first of all, we need to take a look at the weight and volume of the solution used. As you can see, the given mass is 8 grams, while the volume used is 50 milliliters. If you convert that to liters, that is 0.05 liters. So next, we need to find the mole of the solution. And to get the mole, we just divide the weight of the solution by the atomic mass of the molecule. And as you can see, 8 divided by 152 and we get 0.0526 moles. Now in order to find molarity, we just insert these values into the formula of M is equivalent to N over V. And as we get 0.056 divided by 0.05 liters, we get 1.052 as the molarity of the solution. To find the concentration of the FeSO4 solution, we just divide the mass by the volume in liters, and if we get 8 divided by 0.05 liter, we will get 160 grams per liter. So, in conclusion, direct titration is basically a method that involves a reaction between two compounds, which is an analyte and a titrant. And it only involves one chemical reaction between the two compounds, and to get the result, it's pretty simple, as you only need to look at the color change of the indicator used for the two reactions. Now, direct titration is a common method that is widely used in various applications worldwide. Despite the simplicity of the procedure, it plays a vital part in the world of chemistry as a method of determining the concentration of substances. While there are other more advanced methods, direct titration is by far the easiest and also most cost-effective method of testing and execution, hence why it was used worldwide.